Why Ingress is confusing and why it matters. Kubernetes Ingress is one of those components that almost everyone uses, but only a small number of people truly understand. It sits quietly at the edge of a cluster, shaping how the outside world reaches your applications. And while it's often described very simply, it just routes traffic to services, the reality is far more nuanced than that. Most engineers first encounter Ingress as just another Kubernetes object. But once you are running real workloads in production, it quickly becomes something much more important. Ingress becomes the front door to your entire platform. And if that front door is poorly designed or misunderstood, you feel it everywhere. In routing issues, HTTPS problems, scaling headaches, and painful debugging sessions. On the other hand, once you truly understand how Ingress works, something clicks. The networking layers of Kubernetes stops feeling fragile or mysterious, and start to feel elegant, predictable, and genuinely powerful. By the end of this session, Ingress won't feel like magic anymore. It will feel like architecture. And before we dive into Ingress itself, there is one thing we need to do first. We need to understand the problem it was designed to solve. Because once you see that problem clearly, the solution feels almost inevitable. Before Ingress existed, exposing applications to Kubernetes was genuinely chaotic. Every time you wanted a service to be reachable from the outside world, the solution was almost always the same. Create a new load balancer. And each of those load balancers came with baggage of its own. A public IP address, a DNS record to manage, and very often a separate TLS certificate as well. As more services were added, the number of public endpoints grew just as quickly. The cluster stopped feeling like a single cohesive platform. Instead, it began to look more like a scattered collection of independent servers, each exposed in its own slightly different way. From an operational point of view, this quickly became painful. From a technical perspective, it was inconsistent. And from a security standpoint, it was nothing short of a nightmare. What Kubernetes needed was a way to take dozens of potential entry points and collapse them into something far cleaner. A single, structured, intelligent gateway sitting at the edge of the cluster. That's where Ingress came in. Not simply as another tool, but as a unifying architectural pattern. And now that the problem is clearly framed, we can finally ask the right question. What is Ingress actually supposed to be? Ingress is often misunderstood because it looks like it handles traffic. But in reality, it doesn't. At its core, Ingress is simply a declarative set of rules. Those rules describe intent. They tell Kubernetes things like, this is the host name I care about, these are the paths I want to match, and this is the service that should receive the traffic. That's why it helps to think of Ingress as intent, not action. It's much closer to architectural drawings than to a running system. The drawings describe the structure and the behavior you want, but they don't actually build anything on their own. And that distinction matters because Ingress itself doesn't terminate TLS, it doesn't load balance traffic, and it doesn't act as a proxy. What Ingress really provides is a specification for routing, a blueprint that defines how traffic should behave at the edge of the cluster. Everything else happens because of something far more important working behind the scenes. So to understand how these rules actually come to life, we need to meet the component that does the real work, the Ingress controller. If Ingress is the blueprint, then the Ingress controller is the builder that turns that blueprint into reality. It watches the Ingress rules you define and uses them to configure a real reverse proxy, whether that's nginx, traefik, HA proxy, envoy, or a cloud-native controller provided by your platform. This is an important distinction because every capability people usually attribute to Ingress, things like TLS termination, URL rewrites, rate limiting, redirects, and authentication, is actually delivered by the Ingress controller itself. without a controller installed, Ingress does nothing at all. With a limited controller, Ingress is limited as well. And with a powerful controller in place, Ingress becomes a genuinely world-class traffic gateway at the edge of your cluster. That's why choosing an Ingress controller is an architectural decision. It's not just a matter of writing YAML. Ingress controllers are the true engines driving cluster edge traffic. And now that we have identified both the blueprint and the builder, we are ready to follow a request as it moves through the system. To really understand Ingress, it helps to visualize the full journey a request takes, from the outside world all the way into your cluster. Imagine a user accessing api.example.com/orders. Long before that request reaches Kubernetes, DNS steps in and resolves the domain name to a single public IP, the IP address of your cloud load balancer. That load balancer acts as the entryway. It's the point where all external traffic is gathered and funneled into your platform. From there, the request is passed into Kubernetes and handed to the Ingress controller. The controller examines the host name and the path, consults the routing rules you have defined, and decides which internal service should receive the traffic. That service then forwards the request to one of the healthy pods running your application. The pod processes the request, and the response flows back out through the system by following the exact same path in reverse. What feels instantaneous to the user is actually a carefully orchestrated round trip. From the client to DNS, through the load balancer, into the Ingress controller, down to the service and the pods, and then all the way back out again. This continuous flow is the heartbeat of Kubernetes edge networking. One of the simplest yet most powerful capabilities Ingress gives you is host-based routing. It allows traffic to be routed purely based on the host name in the request. That means a single Ingress controller can clearly separate traffic for different domains: app.example.com, api.example.com, and admin.example.com. Even though all of these domains point to the same external IP address, Ingress can treat them as completely independent applications behind the scene. This fits naturally with microservice architectures. Each subdomain becomes a clear, human-readable contract. This is where the front end lives. This is where the back-end API lives. This is where the admin interface lives. Seen this way, host-based routing transforms your cluster. It moves you from a loose collection of pods to a structured platform with intentional, well-defined entry points. That kind of structure brings clarity at scale. But domains aren't the only way to organize traffic. URL path can be just as effective. While host-based routing separates traffic by domain, path-based routing separates traffic by the structure of the URL itself. That's what makes it possible to expose multiple microservices behind a single application. A request for / might be sent to the front end. A request for /API might be routed to the back end, and the request for /auth might be directed to the authentication service. From the outside, users see just one domain, example.com. Inside the cluster, though, traffic is quickly distributed across a set of specialized services. Each one focuses on doing a single job well. This pattern is elegant, it's intuitive, and it's extremely common in real-world systems. Your platform gains flexibility and structure, without forcing users to think about or manage multiple URLs. This is where the idea of Ingress as architecture really comes alive. One domain, one edge, many carefully orchestrated destinations. But routing is only part of the story. Securing that entry point matters just as much. Security is not optional, and Ingress plays a central role in making sure it's enforced consistently. Rather than configuring TLS separately on every individual service, Ingress allows you to centralize HTTPS right at the edge of the cluster. At that edge, the Ingress controller takes responsibility for terminating TLS. It presents the certificates, handles encryption and decryption, negotiates protocols, and manages the secure handshakes with the client. Once traffic crosses that boundary and enters the cluster, internal communication can safely use plain HTTP. This approach significantly reduces complexity inside your services, while still preserving strong end-to-end security for external traffic. And with tools like Cert Manager automating certificate issuance and renewal, HTTPS becomes reliable, repeatable, and largely hands-off. When TLS is handled at the edge, everything behind it becomes cleaner, safer, and far easier to operate. And beyond routing and TLS alone, Ingress unlocks even more advanced behavior through annotations. This is the point where Ingress becomes more than simple routing. This is where annotations come into play. Annotations unlock advanced behavior at the edge of the cluster. They allow you to reroute URLs, enforce rate limits, shape and control traffic, ingest authentication, manipulate headers, and fine-tune timeouts, all without ever touching application code. What annotations really do is bridge the gap. They connect the declarative simplicity of Ingress rules with the full power of the underlying controller. This is how something like nginx evolves from a basic reverse proxy into a fully fledged enterprise-grade gateway. It's how behavior can change on a route-by-route basis, and how real-world traffic requirements are handled cleanly and predictably. Yes, annotations are controller-specific, but that flexibility is intentional. Used carefully and deliberately, Ingress stops being a blunt tool and becomes a precision instrument. And as with any powerful instrument, there are a few common pitfalls worth understanding. Ingress rarely fails because Kubernetes itself is broken. More often than not, it fails because the details matter, and one small detail has been missed. A very common mistake is simply forgetting to deploy an Ingress controller. The Ingress rules exist, they are valid, but there is nothing to enforce them. It's a bit like writing traffic laws for a city, but never hiring any police to apply them. Routing mismatches are another frequent trap. A single missing slash can completely change how a path is matched, and an incorrect path type can stop a rule from ever triggering. TLS issues come up just as often. A secret name that doesn't quite match, or a certificate that lives in the wrong namespace. And then there is the final, easily overlooked detail, the service port. Ingress always forwards traffic to the service port, not directly to the pod port. These problems aren't signs that Kubernetes is overly complex. They are signs that it's precise. And working comfortably with that precision requires one key skill: learning to follow the traffic flow. Debugging Ingress really starts with a shift in mindset. You need to stop thinking in terms of YAML files and start thinking in terms of traffic flow. The best place to begin is always the very edge. Is DNS pointing where it should? Because if DNS is wrong, the request never even reaches Kubernetes in the first place. If DNS looks correct, the next stop is the load balancer. Has it been provisioned successfully? Is there an external IP assigned and reachable? Once traffic reaches the cluster, your focus moves to the Ingress controller. This is where the truth lives. The controller logs will tell you how host names are matched, how paths are interpreted, and whether TLS certificates were loaded correctly. If the controller accepts the request, the next hop in the journey is the service. Is the service port correct? And does it actually have healthy endpoints behind it? By tracing the request end to end, from the edge into the cluster, down to the pod, and all the way back out again, debugging stops being guesswork. It becomes methodical, predictable, and repeatable. And with that foundation in place, we can clear up one final point of confusion: Ingress versus load balancers versus API gateways. All of these tools expose applications, but they are designed to solve very different problems. A load balancer exposes a single service. It's simple, direct, and highly effective when one application needs a public entry point. Ingress takes a different approach. It consolidates traffic, routing requests for many services, through one shared public entry point at the edge of the cluster. An API gateway goes further still. It introduces high-level concerns: authentication, rate limiting, API keys, quotas, and policy enforcement. It often helps to think about this visually. The load balancer is the front door, Ingress is the coordinator in the lobby, directing people where they need to go. And the API gateway is the customer-facing interface, enforcing rules, contracts, and access. Understanding this separation is important. It keeps architectures clean, intentional, and easier to evolve over time. And with that distinction clear, we can turn our attention to what running Ingress in production really looks like. Production Ingress isn't really about writing rules. It's about operations. It starts with choosing a strong Ingress controller, one that runs in its own dedicated namespace, with clearly defined RBAC, proper resource limits, and the ability to scale automatically as traffic grows. Security at this stage has to be automated. TLS should be handled by Search Manager, and DNS records managed automatically with tools like external-DNS. As systems evolve and the number of routes increases, Ingress resources need to be separated thoughtfully, keeping routing rules readable, intentional, and easy to reason about. And observability is no longer optional. You need metrics, logs, and clear dashboards. Dashboards that surface latency, error rates, and TLS handshake failures before users ever notice a problem. Seen this way, production Ingress becomes much more than routing. It becomes governance, security, automation, and scale, all flowing naturally from a well-designed architecture. Picture your Kubernetes cluster as a building. One building with a single clearly defined entrance. That entrance is the load balancer. And just inside, you will find the Ingress controller, acting like the receptionist. When a request arrives, the receptionist reads it, checks the directory, and directs it exactly to the right place. Those Ingress rules are the directory itself. Services become the departments inside the building, and pods are the employees working within each department. Requests flow in through the entrance, the work gets done, and the responses leave the building by following the very same path back out. Seen this way, Ingress stops feeling abstract and mysterious. It becomes the architectural pattern that turns a collection of services into a coherent, accessible platform. We have reached the end of this video. And if Ingress finally makes sense now, not just the YAML, but the architecture behind it, go ahead and hit like so other engineers can find this breakdown. And if you haven't already, do subscribe to AIGURU. Here you will find Kubernetes deep dives, distributed systems explained clearly, cloud architecture, and practical DevOps patterns you can actually use. And before you go, leave a comment below and let me know. What should I explain next? Thanks for watching, and I will see you in the next one.